Did Thomas Crapper really invent the toilet? How did Soviet-era famines give us Tony the Tiger? How did Sigmund Freud's nephew use bananas to start a 36-year civil war? You can learn all about these and hundreds of stories in my new book, Facts That Aren't True. Link in the description.
So, like, obviously, our typical protein has 150 amino acids, right?
Are you, you're telling me evolution can't be true because there are too many non-functional permutations of a protein?
Yeah, I mean, if there's 20 amino acids, so the total number of possible sequences is like 20 to 150, right? So,
Well, if the protein has 150 amino acids, then yeah.
right, but evolution has to like search this space by like incremental steps or like mutations. So, I mean,
No.
natural selection can only preserve what already works. It can't,
Yeah,
it can't plan ahead.
that's true, and that's not a problem.
So, the argument with it will say it can't plan ahead, though, right?
Yeah, I know.
So, if it can't plan ahead, what would your argument be to that?
Why would it? So why would it need to be able to plan ahead?
I mean, not because natural selection basically only selects traits that give a current like survival or reproductive advantage. I mean, it has no ability to plan ahead or build like multi-step structures. I mean,
Yes,
uh,
but there
unless every
are.
intermediate step is also beneficial. I mean, this makes
Yeah,
it
an
inherently.
intermediate step can absolutely be beneficial.
But I mean, it would force evolution to explain every step, not just the end result.
Yeah, I know. It can explain the intermediate steps because the intermediate steps can be beneficial. So, for example, take you know what leaf mimicking insects are?
Yeah.
So when you see a leaf mimicking insect, it's really insane because some of them, they even have the brown spots on them. They have little
Uh-huh.
pieces of their body where it looks like part of the leaf has like decayed or come like not fallen off, but like they're not perfectly shaped, right? They're very convincing leaf mimics, right? And so the idea is evolution has to be able to see that with foresight and progress toward that goal. But uh, but it doesn't because let's imagine um
Uh-huh.
so there are no leaf mimicking insects, but there are insects, right? And let's say that an insect lives on a tree. You with me so far?
Uh-huh.
Okay, and that insect um let's say the insects give birth to absurd numbers of offspring, right? So let's say an insect gives birth to, I'm just going to say 100 offspring. Some of them are a shade of green that's really close to the shade of the leaves of the tree they live on, and others are not. So some of them blend in with the environment better. So the ones that blend in with the environment better have a better statistical chance of surviving and reproducing, and their offspring are going to look more like them, not more like their siblings that don't blend in as well. Does that make sense so far?
It does make sense so far, yes.
Okay. So this insect does not have all of the hyper specific leaf mimicking phenotypic traits yet, but it has part of it, right? And the key is the full leaf mimicking insects don't exist yet. But natural selection can incrementally pick out. I'm saying that it does it consciously or something, which isn't the case. That's just the way we talk about things. But now that the shade of green has been picked out, now an insect that's very slightly flatter than another looks even more like a leaf, and that kind of variation can occur in a population. And so they gradually, this kind of, we call it directional selection, pushes the population, that species or whatever, to become more and more and more phenotypically specialized. But it can happen. The key thing here is it can happen in tons of different ways because there are leaf mimicking insects. There are stick mimicking insects. So it could be the case that in that original population, some of them are born brown. Well, now they're going to live on the branches and blend in better. And once that gets started, then bodies that are ever more slightly elongated, or insects that have a proclivity to stand still more often, are going to be hidden better. And then that just keeps getting more and more exaggerated over the generations.
Okay. I do hear what you're saying. I mean, yeah, if I can grant to you to an extent that when it comes to leaf mimicking insects, that this could be the case. The issue here would be is that if you're saying gradualism works in this case, the problem is that partial mimicry isn't really good enough. So
Yes, it is.
natural selection would not favor it because it may actually
Yes, it would.
penalize it.
No.
It would penalize it.
No, it wouldn't penalize it. You're comparing partial mimicry to complete mimicry. The complete mimics don't exist yet. They're not competing against complete mimics. They're competing against the other members of their species, and the species is moving toward more perfect mimicry, but isn't there yet. So the less than perfect mimics absolutely have a survival advantage over the other even less than perfect mimics. Perfect mimics don't exist yet.
Okay, so if I grant you that with leaf mimicking insects, this to be the case, the question I'd have for you next would pretty much be that, like, are we to believe that these random mutations in selection, basically with no planning, produce this level of precision, step by step, but basically, I mean, the odds of this happening without coordinated guidance is vanishingly small. I mean, that's the problem. Is that, like, yeah, I can grant you, like, with leaf mimicking insects, maybe the case. The problem is that you're saying that with no planning, random mutations produce this level of precision across the board. Because you see it not just in insects, correct?
You see it in everything, but we already walked through the logic of it. Every population is going to have some variation. That variation is not planned ahead, but those phenotypic variations that can produce a statistically better chance of survival are absolutely capable of being selected in the environment, and then that changes the genetic composition of the population, because certain individuals with certain trait expressions statistically survive more often, and then therefore their offspring make up more of the population every generation, and that's what drives the like phenotypic diversity and really it drives speciation. So
Yeah, I mean, but like mimicry, like I would say like mimicry involves like multiple traits, governed by multiple systems. I mean, like, the thing is, like, where's the genetic mechanism that makes this happen? I mean, there's no known like leaf mimic gene, right? So if mimicry involves multiple
there
traits
are
governed by multiple systems, I mean,
very few traits have a gene for them. Like human height is like, it's literally thousands of genes work. Well, maybe not thousands, but certainly hundreds of genes that work together. So there's no gene for human height, but there still are clearly the difference. But the environmental effects of human height are extremely subtle. Now, we don't have the gene for human height, but it's very clearly overwhelmingly genetic still.
right. I mean, I'm trying to think of how to respond. Kind of. I do hear what you're saying. It kind of comes down to, I'm sure you've heard this 1,000 times. This is like a very common fun run thing, but I mean, like, in theory, I mean, like, the likelihood of this happening is the same as a hurricane producing a house, But it's like, in theory, sure, but it's like statistically absurd in practice.
That's because those explanations are always a really terrible straw man of what's actually happening, because those examples, what they do is take a current living organism. Well, I mean, the biggest problem is that it assumes that the process is a random, unguided well, I don't want to say unguided, but it assumes it's a random process, and it's not. What accounts for the variation is random, but the selection is very non-random. We're going to pause for just a second because I want to show everybody this. This is from the YouTube channel Stated Casually. He does evolution educational videos. But here's that leaf mimicry played out in front of us. The idea of, so those guys are not selected for because they don't blend in. The green one blends in. It doesn't look like a leaf yet, but every generation slightly different. That went a lot faster than I thought it would. But every generation, slightly different variations in the population pop up. And then that's how we can get sort of each step in the phenotypic variation over and over again. So I slowed it down. So it's like half of what it was. So there's the idea of how it works right there. So anyways, I just wanted to show that because it's cool.
No, you're fine. I mean, like, obviously the argument always comes down to, yes, what you're saying in practice and demonstrated could make sense. It could make sense, yeah. I mean, but you would agree that like 99% of the mutations are either neutral or harmful, right?
No, I wouldn't say 99%. I mean, maybe it is that, but that doesn't really matter because we have naturals. Yeah, right, even if only 1% of them are beneficial, well, okay, which mutations are going to be selected for? The beneficial ones. So if you have a population of 1 million organisms and only 1% of them have the more beneficial mutations, then they're going to be selected for in that environment. So it can still drive change in them. The only argument you could come up with that is, well, if most mutations are harmful, then that would just cause the population numbers to crash because there wouldn't be enough beneficial mutations for the population to maintain, and so the species would just go extinct. And it's like, okay, let me grant you that that's how it works. We know for a fact that mutations happen, so this must mean that every single population on Earth is dying. That's not the case. So the logic of the argument is just so self-evidently defeated that I don't understand where we're going.
Yeah, no, I mean, the response to that would just be, okay, so like the reason I asked about the 99% of mutations, okay, would be is that, so 99% of the mutations are either neutral or harmful. I mean, and again, we can call it, let's say 90%, just for sake of argument. I mean, we could say that. Also, sorry, my son is opening a bag of chips next to me. I don't know if you hear that or not. Oh, just a moment. Sorry, yeah. So, what I was gonna say is that, so the problem is that, like, for the human brain, for example, okay, obviously this has like billions of neurons. I mean, they're basically wired in time by dozens of gene networks. I mean, a single mutation won't improve intelligence unless it's matched by many others.
Daddy, can you open this?
So yeah, I can open it. Yeah, actually, I might have to get going. My son actually woke up and he wants a snack. But so like, there you go. There's that. I mean, the thing is that a single mutation won't improve intelligence unless it's matched by many, many others. And again, there's billions of neurons that are firing at the same time. So that would, if that's statistically impossible by chance, because you have billions of neurons, you have it's being functioned by dozens of gene networks. So you'd have to.
So you're saying they would all have to be beneficial in the same kind of way?
Correct. I mean, like, if the argument was that 50% of mutations were neutral or harmful, you'd have a much better argumentation. But I believe the consensus in most, like, out there is that 99% are either harmful or they're just neutral. You'd have to have billions of of beneficial mutations occurring to create this network of the brain for mutations. I mean, again, obviously, it all comes down to 1%. Sure, I guess over time it could occur. But.
So that's a good argument. I've never heard anybody say it that way before. If a trait is polygenic, then all of the traits that control for it have to be positive, or it doesn't. So what you're doing is you're multiplying low probabilities. 1% times 1% times 1% times 1% is 0.00000. I've never heard that before. That's a good argument. But I think it falls apart because what can happen is even if a trait is polygenic, all you need is one gene that what's the word I'm looking for? Contributes to that trait. Only one of them needs to change for it to have fairly dramatic downstream effects. Because the thing about polygenic traits is if one of those genes slightly modifies the expression of another gene, that can slightly modify the expression of all the others. So we don't require a mutation in all of the genes that contribute to a trait. We really just need one, and its downstream effects can be really dramatic. I want to say there may be some examples of that, but I can't think of any off the top of my head.
Yeah, I mean, I agree with you to an extent. Yeah, I mean, obviously, like a change in eye color, for example, that's or a specific trait that can just be changed by a single gene mutation. You know, obviously, it can cause noticeable change.
Right.
But obviously, again, the reason I mentioned the brain is the brain depends on many genes working together in highly coordinated ways. Changing one gene can even cause problems because genes often they interact, and a mutation might disrupt other important functions. So that's why it's like when it comes to the brain is very complex, and the changing of a gene affecting or disrupting other functions would mean they would have to perform perfectly. They'd have to be not only beneficial, but almost like they have to be, I don't know how to say it, but properly, but they have to have different layers to that. And anyway, man, I really do appreciate the conversation with you. My son's up, so I have to get going to him, but I'll shoot you a follow. I'll come back if you don't mind.
Yeah, that's fine.
I mean,
I'll just, I was gonna, God, it's making me, we've detected inactivity. I'm literally sitting here talking. So what do you mean inactivity? Another detail I would add to this is, what he's talking about kind of ignores the gradualism. So, human brains haven't always existed. We have ancestors that had, the tissue is the same, and even the genes that control for it are still conserved. We know, thanks to embryonic experiments, that you can literally take a patch of tissue from the embryo of a completely different species. Like it can literally be, you can do amphibian to chicken transplants. So I can take a patch of tissue from a developing embryo in one species, transplant it onto the other species, and it'll trigger that species to wherever you did the patch, grow that kind of tissue. So you can take frog embryo tissue and from where it's going to develop a limb and put that on a chicken embryo, and the chicken will grow a chicken wing in a place that it's not supposed to, for example. Kind of lost my train of thought with that. But anyways, it kind of ignores the concept of gradualism. But the other thing is there have to be all these mutations that all work. With simpler organisms, what we consider simpler organisms, one of the facts with them is they tend to breed in massive numbers. So, for example, insects or many other types of invertebrates. Well, for organisms like us, we don't breed nearly as much. Same with most vertebrates except for fish. So there is kind of this good line of reasoning that says something like, well, we can't afford to just do all these kinds of crazy permutations of the traits because the odds are that's going to produce something that doesn't necessarily work nearly as well. But something we know about species is some species have highly conserved genomes and other species don't. And the species that do not have highly conserved genomes tend to be ones that are more simple and reproduce in incredible numbers. There can along the way in the story of evolution, there can be the not concept of, but the fact of genomic conservation would be the word. I don't know what the term for it would be, but the evolution of the genome being more conserved can appear, and then in populations or species, I should say, that don't reproduce in as huge a number, and then this problem isn't really that much of a problem. So hopefully I articulated that well enough that it makes sense.